The video you're about to see is a real-time recording made at a live ICRI technical session. It is important for you to realize that the remarks of the speaker do not necessarily represent the views of the International Concrete Repair Institute. This presentation is intended to refresh your memory if you attended the session and to allow you to benefit from the speaker's remarks and from the question and answer period if you were unable to attend. Now here is the introduction to the speaker for this session.
I have the pleasure of introducing our speakers throughout the course of the morning. I think we've got some great topics and some very good and interesting speakers for you to listen to. I'm sure most of our presenters will leave some time at the end of their presentations for any questions and answers that you may have. Leading off this morning is Peter Emmons. Peter is the president and founder of Structural Preservation Systems, specialty restoration contractor who's been around for a long time, and they do some great work all across the country. Peter has 27 years of experience in the repair business. He's a past president of ICRI. He's on several committees, both through ACI and ICRI. So Peter, with that, we'll lead off. Peter's topic is corrosion protection in concrete repair, myth and reality. Good morning. What I'd like to do today is spend a few moments, next 40 minutes, talking about some of my experiences with corrosion as it relates to repair. It's also going to delve into new construction because there's some perplexing issues that we find in repair that should really be solved in the new construction side of the business. I'm going to be talking from a contractor perspective. And as you can see on this slide, there's many different perspectives that are going to be given to you today from the material people, the engineers, the contractors, and some owners. And certainly these perspectives need to be understood so that you can understand the biases. Everybody has a bias in this business. You know, the owner wants the cheapest, most effective repair. Contractor wants speed, he wants to make money. Engineer concerned about the risk of his design. You know, he's looking for performance. And of course, the material producer is looking for innovation. You know, the one-upsmanship. He's got to develop technology that he can sell, and he certainly wants to make a profit like all of us. You know, this whole business about corrosion and repair starts with this type of thing, pretty common in most parts of the country, most parts of the world. You know, it's all about this rebar and other embedded metals, where these metals want to go back to the way they were found in the earth to begin with, as an ore, an oxide. And these oxides expand, as you can see in this particular slide. You know, that's the corrosion product that we'll be talking about for the next 2 days. You know, this corrosion product expands and creates tremendous forces. And these forces are tremendous, and they can do what you can see here. They can delaminate the concrete, and that's what this is all about. And as Joe Solomon said earlier, this is billions and billions of dollars being spent by us, the owners of these structures, to fix and repair these structures. So it's a great business. If you're in this room, most of you are profiting from this repair business. And we develop technologies, materials to fix these things, and you're going to hear a lot about this today. You know, what the effect is, the spalling, the corrosion, all kinds of strategies, means and methods and tools. It's pretty exciting because there's lots of neat innovation going on in this business, and a lot of it's related to the corrosion issue. And we're going to be spending a lot of time this morning in my talk just talking about some of these repair strategies, some of the things that we're doing, and I'm going to just raise some questions and some food for thought, because there's lots of issues with these different technologies. And it's important to understand these issues so you, the user, can ask the right questions when you're presented with an opportunity to use some of these technologies. We've learned a lot about corrosion over the years. We know that the corrosion process is not just you need some water. You know, it's amazing how many times back in my earlier years in this business I thought you needed water was getting into the concrete, water was causing the corrosion. Water is just a part of the process. certainly oxygen and water, but we've also learned that chlorides and carbon dioxide are the two key elements. So you need certain things for this reaction to take place. That's something that we've learned. We've also learned that this process is an electrical process, something that's really at the fundamental level very hard to see. These are electrons flowing, and we're going to hear some of the things that, some of the theory from some of the speakers later today and tomorrow. I know Dennis Pinnell and Gordon Gu are going to talk a lot about the theory and some of these issues so you can understand or get confused, as I do, when you're talking about electron flows. We've learned a lot about these chlorides. You know, chlorides are great for our business, and we've learned a lot about where these chlorides come from. Some of it's coming from the outside, like road salts. You know, where we have cold weather, we put a lot of salts on the road, and those salts come into the structure via vehicles and so forth. Some are airborne. If you're on the ocean front, salt water, we were just talking before the meeting in Hawaii, they've got all kinds of airborne salts in the air. They have also got a lot of aggregates that they use in their concrete mix that have got a lot of chloride in it. So we know that there's different sources of salts that get into the structure. We've learned over the years that the wonderful admixture that was used to accelerate concrete, calcium chloride, has created a lot of nice work for us. And most areas of the country prevent the use of those materials where there's going to be reinforcing steel. But in other parts of the world, we still see some of the use of these materials because it's a cheap accelerator. We've also learned, maybe we're the latecomers in the United States, about carbonation. In Europe and other parts of the world where they have more mature structures, we know that carbonation, the gas in the air, is causing a lot of problems. It's a natural event that takes place where the alkalinity of the concrete, the natural protection for the reinforcing steel, is being lost to this acidic attack. We've learned that you can put different indicators. This is phenolphthalein on the surface, and you can see the level of carbonation. Anything below a pH of 10 is clear. And you can see in this particular, this is a soffit of a balcony slab in Florida, 15-year-old slab. The depth of carbonation is about 1.5 inches. It's about 1 millimeter or so a year penetration right through a coating. This is a coating on the surface. It's really interesting to note that carbon dioxide goes right through this coating, right through this mortar surfacing that levels off the surface, right into this concrete, and travels right back into the concrete. It's looking for this reinforcing steel. Once this carbonation level goes back to that reinforcing steel, you have lost the alkalinity, the natural protection. So now water and oxygen can cause corrosion. You can see also that this crack on the surface that penetrates this slab allows the carbon dioxide to penetrate deep into the structure. And you can see the white area around the reinforcing steel where the crack crosses that bar. So we've learned a lot about that in the United States, and that's going to be a future problem that we need to be working on. Certainly this exists today in the United States, but we're going to see a lot more of it in the future. There are some new tools available. This is something recently we found as a pencil. It's a simple little pencil, and you rub that across the surface of the concrete, and you check the color, and you can check the level of carbonation. Pretty neat. You don't even need to spray chemicals. Something else that we've learned about these materials, the chlorides and the carbonation, is that you can run tests individually on the carbonation level and on the chloride level and find out they're both within acceptable limits. But if you add them together, you have a tremendous synergy between the two. So you can have a very high pH where the concrete would come out pink in the phenolphthalein test and have very low chloride content. A low chloride content by itself would not promote corrosion, but you add the two together, we have tremendous levels of corrosion taking place. So it's very important to find out exactly what the levels of these two things are in your structure if you're doing an investigation. Because we've seen errors where they look at the chloride content alone and find out the structure is just fine and don't really treat the cause of the effect. I'd like to talk about preparation. Probably one of the most important things that we've learned in the last couple decades is preparation. Preparation can lead to very successful repair work. I'd like to talk about a couple issues. One of the things that was pretty prominent in this business a couple decades ago was we didn't chip behind the bar. We just knocked the loose stuff off. You really didn't need power tools. You go on the surface of the building, you take a mason's hammer and knock the loose stuff off, and then you went with a mortar and you troweled it back. No power tools, maybe some wire brushes. These type of repairs, where the repair was done without chipping behind the bar, failed. And I think anybody that's been in this business has seen this. And one of the things that we've learned is you got to chip behind the bar. One of the first guidelines, the first guideline this association put out back in '89 was the preparation guide for reinforcing bars that were corroding. And this guide talks about chipping behind the bar. So it really has helped the industry move forward. You go to other parts of the world, like India, for an example, and I've talked to contractors and engineers over there, they don't chip behind the bar. Their repairs don't last. So it's a very important issue that we've learned, and we should not forget it. But it does cost money. And if these guides, if you haven't seen these things, they're available out on the table, and certainly you can take them with you with a few bucks transferred. This is a typical example of some of the type of problems you might see out there, where the tendency, if you want to do it at low cost, is just knock the loose stuff off, wire brush the surface, and trowel it on. If you do that, you end up with things like this. These are very short-term repairs. This repair was done without chipping behind the bar. It lasted no more than 2 years. These are very tempting to an owner looking for the lowest cost. And it takes, in this particular structure, the owner had to do repairs 3 times before he decided to spend the real money and do the job right. These are just some more examples of what it looks like when repairs fail. Another thing I'd like to talk about in preparation, and as a contractor, we have been put in a vice. We've been asked to bid these jobs lump sum, which is a very risky business. And we go out there on these lump sum jobs, and we go out there with a hammer, and we sound the surface, and we do a delamination survey. We get a quantity from the delaminations, and we put our price together. We add 10% to those quantities. Well, in the last couple of years, we've been burnt. Almost every time we do that, we get burnt because we end up with these structures. This particular structure is typical, and maybe other types of structures. Typically, if you're using lightweight concrete in your structures, the laminated area, the area that's hollow from the pressure of the expanding reinforcing steel, is not indicative of the level of corrosion, because many times in these types of structures, the lightweight aggregate actually absorbs the corrosion product. It's absorbed into the lightweight aggregates. They're very porous. So it doesn't build up the pressure to cause delamination. So you can do a delamination survey, and you think you've got a reasonable area for repair, and you go out and you start chipping, and you follow the corroded bars, and your areas might double. Something very important here. If you're an engineer doing the survey or you're a contractor bidding on this work, you really need to understand what type of problems you have. Maybe a pilot test may be appropriate. We talk about reinforcing steel. Once we've exposed these things that have caused the problems, there's lots of issues, and you're going to hear a lot about it in the next couple of days. The repair of the bars, the coatings, there's all types of products on the market that repair bars. First, before I talk about repair, I would like to talk about new construction. New construction, over the last 20, 30 years, they've developed technology to prevent corroding bars. I guess in the 60s and 70s, they talked about galvanized bars, and then in the late 70s, they started transferring the technology to a fusion-bonded epoxy coating. And the value of those systems were to electrically insulate the bars. So if they're electrically insulated, then we couldn't have an electrical process going on. And that's pretty much the state of the art for new construction in bridges. And certain states have banned the use of these technologies because they've had some problems. And I think the state of the art right now is advanced to a point, as you can see in this particular case, they use epoxy-coated bars in the columns, and the ties are uncoated. And I still haven't figured out exactly why that is. And I think that's true with a lot of technologies. We start applying these technologies, and then they start getting abused and misunderstood. And that's somewhat happening in our repair side. In the repair side, we have a lot of issues, and I'm going to talk about a few of these as they relate to repair, and I'll go through some of these in the next few slides. The first issue I'd like to talk about is the repair. A repair is part of the structure. It's not the whole structure. And there's a big difference between new construction and repair. And you can see this bar has been exposed. This particular specification required white metal. That's why it looks so clean. And if you ever try to blast a bar to white metal, you'll realize how hard that is to do. It's almost impossible. But this bar, think about this bar. You can see this bar, but then it disappears. But there's a bar in that concrete. And what I'd like you to do is visualize that bar as being continuous. So it's kind of ludicrous when you start to think about it. In the new construction, we want perfection of these epoxy-coated bars from end to end, tip to toe, stern to bow. But in repair, we can only hit the bar in the repair zone. So does it make sense to encapsulate a bar in that repair zone and leave the bar uncoated as soon as it leaves the repair zone? And then we deal with the constructability of that. How do you coat, I'm talking about epoxy coating now, where epoxy coating is an electrical insulator, and for electrical insulators to work, they have to be perfect. If you have a pinhole in it, you concentrate electrical currents. So an engineer that specifies this wants a pinhole-free, perfect coating system. But as a contractor, I can tell you it's very difficult to do this. On the back side of the bars, it's very difficult. Where bars intersect, you have two number 8 bars lapping each other. You know how difficult that is? It's almost impossible. They're touching. There's going to be a gap there, uncoated. So it really brings into question the issue of the practicality of it. Especially as a contractor, we're the ones at the end of the chain where there's a specification, and the specification requires these things. It's very costly to do these things. A recent job we did in the Baltimore Aquarium, the cost per square foot was close to $6 a square foot to blast and coat the bars because of the requirements of white metal, pinhole-free coating systems. There are other systems available. There's lots of systems. Lots of manufacturers in the hall next door make products to address these issues. In general, what I see is the epoxy coating systems have fallen out of vogue for repair and have led to different specialty coating systems that are based upon either the alkalinity protection. The alkalinity of concrete is a natural protection. It has a high pH, and that high pH is what protects the concrete. It causes passivation of the reinforcing steel, and it really protects the bar. So some of these systems are basically the alkalinity, similar to concrete, in a coating form that's applied to the bar. There's sacrificial zinc systems that are really passive cathodic protection systems that have been around a long time. And of course, we'll be talking a little bit later about the impressed current cathodic protection systems. What I just talked about earlier was the epoxy coated, the field applied epoxy coating system. And it's my view that we want to keep these repairs and the design of these repairs as simple as possible. There's less to go wrong. It's not that we want to do them with less work. We want things not to go wrong. And we know and we believe totally in Murphy's Law that the more you do, the more is going to go wrong. So our preference is to use the natural alkalinity of the repair material. If we're using concrete, use concrete. We don't have, in the last 27 years, we've never seen a failure of our repair due to corrosion within the repair material or where the repair material comes in contact with the reinforcing steel. There's a lot of issues with these coating systems and the whole repair system, and there's going to be other speakers today and tomorrow, especially Gordon Gu and Tate Coverdale, and I know Dennis Pinnell is also going to talk about this. There's a lot of issues with compatibility, electrical, chemical compatibility of the repair systems, and you're going to hear a lot about this ring corrosion, where the theory is the repair is causing the electrical current to concentrate right onto the outside of the repair and will cause accelerated corrosion. I'm not going to really comment on this, but there's a lot of theory and reality to this. As a contractor, we certainly see failures outside the repairs as the years go on after the repairs are installed. you see deterioration taking place outside the repair zone. And the real question is this just a natural progression of the deterioration process? The same process that caused the problem to occur originally in the repair zone is now moved to the outside? Or is this the accelerated corrosion on the perimeter? And these are difficult things to really put our hands on because it takes time. And time is what's really giving us the problem in understanding these mechanisms. The other issue I'd like to talk about as it relates to these coating systems is, for these rebars, is that the test data that the manufacturers use are generally applying a test method that's used for new construction. There are test methods. If you have these epoxy-coated bar systems for new construction, they have a ponding test that ponds salt water and they measure the current flow in the bars beneath. And I know Dennis and some of the others are going to talk about this specific test. But this test method is really designed for new construction. This does not simulate a repair situation where you have a repair material and existing concrete that's contaminated. So we get test data that supports the use of these products that's based upon new construction. And we have to be very careful applying these types of things to the repair situation because they're not necessarily indicative of the situation, and nor will they guarantee performance. And I think that's really one of the important issues you need to walk away with is test methods. There's lots of test methods out there. We can produce data that can show almost anything you want to see, and that test data can influence your buying decision. So it's important to understand these test methods and understand the applicability of these test methods to the repair situation. So I think we've covered most of these issues, constructability, costs, the marketing issues. Manufacturers are there to bring new technology to you, and they're going to push the envelope many times. Many times these products will come to market before they're out there tried and true. And many times we're the guinea pigs as the users, which is okay as long as we know that. Because that's the only way these new technologies will be, we'll find out which technologies work. Galvanic corrosion. Another process that we find in concrete structures that we end up repairing is caused by different metals within the concrete, aluminum and steel and so forth. Those things set up a galvanic cell and cause corrosion to take place. And one of the things that we've learned, and it really pertains to new construction, but certainly in a repair situation, is electrical conduits. Electrical conduits should never be installed in the slab where the slab is going to be exposed to the elements, like a parking structure. I was just up in Vancouver earlier this week, and I saw a new condominium where the slabs came out to the edge, and they got intake air ducts cast right into the slabs. So what's going to happen is the weather's going to come right into those ducts, and it's going to cause all kinds of water intrusion into the slab, and it's going to cause all types of problems. It's crazy for new construction to be using this type of technology. But you can see the corrosion of the electrical conduit. The bar right next to it is in great shape. You can have the same metal, but the different alloys, and you'll have a corrosion cell set up. Just some more examples of electrical conduits and slabs. It's crazy. We see a lot of this, especially in high-rise construction. The slabs are put out there for balconies, and they use a lot of aluminum for the railing systems. In this particular structure, there's an aluminum railing system coming down into aluminum box out. There's aluminum tubes that hold the box outs together so that the alignment is perfect. These types of things are happening. We learned back in the 50s that you shouldn't put aluminum in concrete where they're going to be exposed. But somewhere between the 50s and the 80s, we lost that information from one generation to another. So structures are being built today like this, causing millions of dollars in repair work. It's great for the repair contractor. This particular structure is seeing $3 million worth of repair work. This one structure, $3 million to take care of this one little detail. And why is it that the original designer, the original structural engineer, the concrete contractor, the aluminum rail contractor, the aluminum rail producer, and all those people, hundreds of people were involved in this particular structure, but none of them said anything about this aluminum being in this concrete? It's crazy. So in a repair situation, you've got to know what's going on here. You've got to learn that this aluminum and steel doesn't mix. And the repair situation, the repair design's got to deal with that. It's got to take the aluminum out, or it's got to isolate it electrically so that we don't have those problems. Let's talk about cathodic protection. You're going to hear from a number of speakers, Ollie, Steve Daly, Peter Rubby, and Bruce Collins, different aspects about cathodic protection. And there's a lot of neat technology. It's very sophisticated. It's trying to fool the electrical current, basically. You're taking the current and you're fooling it so that it doesn't cause corrosion of the reinforcing steel. These systems have been around a long time. They're generally, they cost some money. But there are some risks, and we've certainly seen them as a contractor. These systems don't always work. And one of the things I'd like to point out with any of these technologies is that you've got to know the downside. We talk about features and benefits all the time when we're looking at new technology. Here's the feature, here's the benefit, this is how great this system is. But if you're a user, you better ask some important questions. What's the worst that can happen if I install this system? What's the worst that can happen? And in cathodic protection systems, you can totally destroy a structure if it's installed, designed, or maintained improperly. And because these systems generally are sold on a 25-year payback, and maybe some of the cathodic protection people here will take exception to that, but that's what I've heard them say. It takes 25 years to pay back, get a good benefit from these systems. So you have 25 years, these systems have to operate properly. And when you're pumping electricity into the structure, you've got to make sure it's going in the right places and doing the right things. And in one of the structures we recently fixed that was cathodically protected, the system didn't have proper continuity, and the continuity resulted in accelerated corrosion cells, like one of those tests in the lab where you're trying to accelerate the corrosion. It totally destroyed the structure. The slabs had to be removed. So here a system that was installed to prevent this actually did the opposite. So it's very important. All you have to do is ask the question of the salesperson coming to your office, what's the worst that can happen if the system doesn't work properly? If he said to you, well, if it's not maintained properly, or it's not installed properly, or it's not designed properly, we can totally destroy your structure, the owner's going to say, well, tell me about that. In this particular case, the contractor that installed the system, he had to pay for a lot of this the replacement. He took the liability. Inhibitors. You'll hear a lot about that, and certainly it's become very popular in the repair business in the last couple of years. Inhibitors are a neat technology. Here's something so simple and relatively low cost that we can add to the existing structure or into the new material that can really help us, in theory, deal with the corrosion problem. It's pretty exciting stuff when you think about it. Something coming out of a can like that, sprayed on the surface, that can actually inhibit corrosion. In the October issue of the Concrete Repair Bulletin, Rick Montani wrote an excellent article on this technology, but I made a slide of one excerpt from that article, and I think it's really important, and I'll just read it here on the bottom. Inhibitors are finding their fit, not as a panacea for all corrosion problems, but as a way to buy time and extend the life of structures. I think that's really important. None of these technologies are perfect, but they all have some benefits, and they all possibly can extend the life of the structures. But what we have found with inhibitors, and I think this is the point I'd like to get across to you, is, and it's because I've asked the questions, what's the worst that can happen? How does this system really work? How long is it going to last? And those kind of questions, that I've really come to question some of these issues. How long, if we put these migrating inhibitors into the structure, how long will they last? And I would ask you, and ask maybe the speakers that are going to talk about inhibitors later to talk about this. But what the answers I've gotten back from the manufacturers are maybe 3 years, maybe 5 years, maybe 7 years. We don't know. We don't know how long they will last. So here's a product that we're putting in the structure to enhance the value of this structure, but we don't know how long it's going to last. And then I ask the question, how do I measure whether it's in there or not? Okay, so if I can believe that it's not going to last forever, then I need a system to monitor the penetration of this material and see if it's still in there. So the question I ask is, how do I measure it? Well, you take a core and you take that core to a very special lab. There's only a few labs in the world that can measure that. And maybe things have changed since I got that answer, and maybe some of the speakers can address that. So here we have a situation is we don't know how long it's going to last, and it's very difficult to measure. It's not something we can do in the field. So the issue comes, if we want a system that's going to last, what's the cost effectiveness of this? And really, the bottom line that I find out a lot of things is when I ask the question of the supplier, what kind of warranty can you give me? You're saying this is going to last 5 years, it's going to prevent corrosion. In some cases, they've even said, you don't have to chip behind the bar. I say, well, that sounds great. That's going to save me a lot of money, but are you going to back me up when this thing fails? Are you going to give me the warranty? And to this date, I have not received any such warranty. And that's really the proof of this thing. If we're not willing... Hello. I'm getting too excited, I think. Yeah, we're basically discovering the technology together as a team, and that's what I think we have to realize with some of this technology. And inhibitors, I've come to the conclusion is we don't know all the answers, but if we don't go out and try it, we're not going to know whether it really does work or not. And it seems to have a little bit of downside risk. So it's something to try. I think a lot of you guys have negative thoughts out there for me. Concrete cover, that's a big problem. And it's a big cause of many premature corrosion problems in structures. And there's a lot of different technologies, a lot of different strategies to deal with this lack of cover. And I've just listed a few here. You put this low permeable material in there. You can increase the cover. You can remove the bar. You can put these bar coatings on it. You can put coatings on the outside. There's lots of neat technology out there to deal with this. And these are just some of the few. And it really surprises me when the state highway does something like this on a bridge pier. They've got these bars that are too close to the surface. They want to meet their own design requirements. So they build out the repair area, and they even put a coating on it. I just can't believe the governor of that state would allow such a thing. What is wrong with that structure from an aesthetic standpoint? So I think there's better technology out there to deal with these issues, but that's not an uncommon thing to see going down the highway. We see it on buildings. In some cases, the client doesn't have a lot of money. He just knocks it off and puts the coating. He skips a step. But if we're looking at his concern with safety, public safety, stuff falling off a building, you got to make it safe. He made the building safe. He stabilized the condition. It looks like hell, but this is not an unusual strategy. We were talking earlier about a structure in Hawaii that's got cast-in chlorides. And the owner went through and knocked all those stuff off. It looks like, as it was described to me, like Beirut. But what really surprises me, and this is not in our field, not in the repair side, but why is it in new construction there's nothing there to ensure that these bars are placed with the proper cover? There's nothing in the building code that requires any investigation as to the depth of these bars. I guarantee you, if the contractor had to give back money for future maintenance, he would ensure that these bars were placed with proper cover. Recently, we were asked to look at a very important concrete structure, and I underline very important. This structure was built brand new, and they had these little recesses between the form panels. And the specification called for this surface to be sandblasted to a nice exposed aggregate look. They did that. And at these recesses where these little these form strips were put in, certainly the sandblasting operation removed some of the surface, maybe an eighth or a quarter, heavy sandblasting, exposed some bars. So the owner's looking at these things and saying, there's not supposed to be bars right there. He says there's a 2-inch requirement. So they started looking at this thing, and they hired a testing company to come out, and they did a picometer survey, which is just one of those magnetic things. You go through the structure and you determine the location of the bars, how deep they are if you know the size of the bar. So they mapped it out, and they found 450 locations where the bars were too close to the surface, from 0 to less than 1 inch. The specs called for 2 inches. So what they came back to the contractor and they said, what are you going to do about it? This is a big problem. Here you got a brand new structure. They determined, this is one of those unusual owners that found out he had a problem, right when it was being built. So what do you do about it? Well, they cut some of the bars out, but all the bars that weren't on the surface, but what we're going to see, the concern was carbonation. Carbonation is going to move back through the structure. They couldn't put a coating on the structure because that's going to change the aesthetics. A coating will be an effective barrier for carbonation with the right coating system. So what do you put some of these inhibitors on? This is when I found out about these inhibitors. These inhibitors were a good strategy. Let's put some of these inhibitors in the structure. We found out maybe the life of those inhibitors is only 5-7 years. But the problem we're trying to prevent is 25 years down the road, because the owner of this structure expects a maintenance-free, corrosion-free structure with the 2 inches of cover, if it was built that way, to last at least 50 years. So the question I have is not for the guys in this room, it's for the next meeting that follows this, which is the ACI meeting. Why isn't there a requirement to test and verify the cover of these bars in structures that are exposed to the elements? The contractors would do a lot better job. They wouldn't look the other way when the bars are too close to the surface. This is the biggest problem we have in the industry from a new construction standpoint. We have all these requirements for testing concrete for its physical properties, right? Every job requires it. The building code requires taking strengths tests. All we have to do is add one more line in there, and we can eliminate part of our business. But it would be good for the industry to be able to correct a problem that's so easily corrected. These are just some examples. These bars are too close to the surface. Certainly the guy putting the formwork up knew that when he shoved the form in there and the bar was pressed up against the surface. There's really no excuse for these type of repairs. Post-tension. There's a lot of post-tension structures out there, and if you're in that repair side of it, it's a great business. These are structures that are built with these cables that are stretched with a lot of tension. There's a lot going wrong with these structures. Water's gotten into these systems and caused corrosion. And just to point out that there is a task group here at ICRI that's dealing with the issues associated with these types of problems, and they meet at 1:30 this afternoon. So if you're interested, I recommend that you attend and participate and just see what's going on in the task group. But one of the things that we have found is that with these systems, what we thought originally was that there'd be telltales. When these cables broke because of corrosion, they would fly out of the slab. You'd see these big protrusions, cables, and things that are hanging out of the slab. And we said, oh, that's good. We know when they're failing. We know when they're failing. But what we have found over the last couple of years is that most failures have no telltale. They don't show themselves. They just break. They probably break not quietly, but they break unobtrusively. They break and they stay within the structure. And that's pretty scary when you think about it. Here we have a time bomb taking place. We have a cancer within the body of the concrete without any knowledge. It's very hard to investigate these things. So it's something that we need to develop systems for that will be able to monitor and make these structures safe. And one of the issues is that, the Post-Tensioning Institute, which is the guiding body for this type of construction, has a bias. We've seen this clear bias. They have a denial that this is not a problem. We don't have a problem, they keep saying. It's only isolated to, I think it was Calgary, right? The guys in Calgary? It's only in Calgary that we have this problem, but we've seen it all over the United States, wherever these structures are built. So it's important that we deal with these things honestly, and we want to make sure that the structures are safe and that we develop technology to fix these things. So this is an emerging industry. A lot of neat things to do to fix these structures. I'd like to end on a couple things that bother me, and they're questionable repair strategies that are being used because they offer some perceived benefit, maybe low cost. And I'm talking about repair strategies that deal with this corrosion problem. And I'm going to show you a couple examples: epoxy injection, this composite material wrapping structures that have got corrosion damage, and some of the coating strategies that are being used. Talk about epoxy injection. Epoxy injection has been around for a long time, since the early 60s or before. This is a technology of pumping epoxy, and certainly it's, there's some people over here that make equipment and materials for that. You can talk to them. It's a great system. It's a simple system. It's well accepted as a system of re-gluing concrete back together, or waterproofing concrete in some cases. But we find many contractors out there saying that they can fix concrete that's corroding. A lot of these cracks are not just from movement. A lot of these cracks that form in structures are a result of delamination. You know, delamination shows itself on the surface as a crack. And if you have a crack, some contractors are out there saying, yes, we can pump epoxy in there, we can glue it back together and solve the problem forever. From our experience, certainly you can pump epoxy into these cracks. Certainly it costs a fraction of removing this concrete and doing a proper repair. But what we have seen time and time again, these don't last. They'll last a couple years and then they'll redelaminate because the epoxy cannot change the environment totally in that crack. Certainly you can fill up the crack and remove some of the oxygen, maybe displace some of the moisture, but the process is going to go on. And that investment dollar that's been made with this technology is going to be wasted. Maybe you can buy time. Maybe what this system should be sold on is hey, this is going to last you another 18 months. But don't sell it on the basis this is a permanent repair. Or how about this situation? You know, every time there's a new technology that comes on the market, we start looking for uses. It's one of those, hey, I got a solution looking for a problem type of thing. And we have the situation where we have, you know, typical delamination. This is a bar inside corroding. And what's happening is we have new technology on the market. And there's going to be some discussion about that. Craig Ballinger tomorrow is going to talk about it. There's going to be some discussion with Mike Thomas, I think it's University of Toronto. He's going to talk about that. Is it tomorrow? Yeah. Here it is, tomorrow morning. Uses of advanced composite material wraps for repairing corrosion-damaged concrete columns. This is really scary, guys. They're taking this technology that was developed for strengthening structures, and it's very good. It's good material. We've had good success with it to strengthen structures. But when we're taking this material and we're saying that we can contain the forces of this corrosion product by wrapping these high tensile capacity materials around the structure, we're really treading on dangerous water here. And again, this is a solution looking for another market. And this is what we have to guard against, because if we go out there and start using this technology to contain these forces, it's a very high risk business. Certainly we can put enough carbon around a structure to contain these forces, but what else is going on? Is that bar still corroding? Is that corrosion product building? Is the bar disappearing? Are we going to have a structural collapse without any warning? These are the issues we're faced with. Certainly, we have to guard against that. This is just an example of a steel plate around a column. You can see that crack coming down it. The steel plate was wrapped around it, and the expansive force of that crack caused that plate to split. Just to give you an idea of the forces involved. So I challenge you to ask the questions when you see these technologies being presented to you as panaceas, as the newest solution, the newest innovation. We need to understand what they're all about. And certainly this paper tomorrow will discuss some of the things. There's doing some research with this technology, but ask some tough questions of the speaker. What's that? You're going to get even, Greg? We're going to get even with you. We see specifications on buildings to put sealers on these buildings, and sealers and coating systems are really good to protect the structure from future deterioration. But one of the surprising things that we have seen on buildings is the specification where we're putting a silane sealer on the structure. This is a structure we've just fixed, and they're specifying a sealer to protect the structure. And when you're putting a silane sealer on the structure, what is it you're really doing? Well, are there chlorides? Is this a carbonation problem, or is it a chloride problem? If chlorides are coming in from the ocean spray, maybe the silane sealer is going to do a good job. But if we're dealing with carbonation problem, what is that silane sealer actually going to do to protect that structure? So we have specifications saying that we should put sealers on the structure, silane sealers, which are really chloride screens, they're not carbonation screens, to protect the structure. So I really question, the selection of these type of sealers for something that we're trying to remove, which is the cause of the problem. And certainly there's maybe some manufacturers in here that can address that either in their booth or in an answer to this question at the end of my talk. I stole this from the bulletin. It was an advertisement from one of the booth presenters. I thought it was really good. Some things were meant to crack, and certainly our repair material is not designed to crack, but it does. It's a problem, and we've talked a lot about that over the years. And certainly when a repair material cracks, it opens up a canyon for these materials to go right back into the reinforcing steel. So we have an issue with that, big issue. So no matter how good this material is between the cracks, it's absolutely worthless if we have cracks in it, if the cracks allow the moisture and salts to penetrate it. So I started out by talking about these perspectives. There's many perspectives, there's many issues. It's actually a pretty exciting thing because we're on the verge of understanding a lot of these things, and there's a lot of questions to be answered, a lot of questions to be asked. And a couple things I'd like you to remember when you're using these technologies is that there's lots of data out there. The data can show you anything you want to see, absolutely anything. So you need to understand the data, you need to understand the test methods. There's also a law that I always believe in that if it's something really good on one side, there's something you're giving up on the other. These are important things to remember. These are some of the risks that you're involved with as a contractor, a material supplier, engineer, and certainly the owner who's footing the bill. Thank you very much. I ran out of time. No questions, thank you.
Steve Bailey with Corpo. Peter, I disagree with your statement regarding product protection where you indicated that the structure could be completely destroyed as a result of discontinuous rebar. In the case of an impressed current system where you have a rectifier, if you connect the anode to the wrong terminal on the rectifier, yes, then you can accelerate the corrosion dramatically. In the case of high-strength steel, you can have problems if you exceed the voltage for hydrogen embrittlement on high-strength steel. But discontinuous steel is typically not a big problem with bridges. It can be a problem with parking structures. It should be connected in properly, but the voltage gradients are so low with these systems that the corrosion can be insignificant to create tremendous problems like you're referring to. I would suspect that the problem is just related to the fact that the system wasn't operating and it went back to its native state of corrosion activity.
Yeah, Ali, you want to address that?
Yeah, I disagree with Steve. If you use the guide protection incorrectly, you can destroy a structure, and I can show you examples of it right in Washington, D.C. It had so much discontinuity that even at the low voltages, whatever current that flows out of the bar is going to cause an equal amount of metal loss. And it can do that if you improperly install it. And in press current systems, you have a higher chance of doing it because you're putting on far more current than you are doing in a galvanic system. But yes, most of the time the problem is in parking garages rather than bridges.